Welcome back, everyone. In some of our earlier videos, we talked about our trigonometric functions and how they can be used to help us work with and solve problems involving right triangles. In this video, we're going to keep working with our trigonometric functions and see how they can also help us solve and work with these non-right triangles. And so if a triangle is not a right triangle, we call it an oblique triangle. And so really there's kind of two flavors these oblique triangles come in. They either are going to look something like this, where all three of the angles in our oblique triangle are acute angles. That means they're all small angles less than a 90-degree angle. And so the other type of oblique triangle that we might encounter or run into is the kind that contains an obtuse angle or a large angle that is larger than 90 degrees. And so in this video, we're going to come up with a formula that we call the law of sines, and that's going to help us relate the side lengths to the sine of the angles within these oblique non-right triangles. All right, before we derive that formula we call the law of sines, let's go ahead and remind ourselves of the standard labeling convention for a triangle. And so we reserve capital letters for our angles. So this is angle A, up here is angle B, and there is angle C. And opposite of every angle, we label the side length of that angle with the corresponding lowercase letter. So opposite of angle A will be side length A, opposite of angle B will be side length B, and the side length that is opposite of our angle C is what we call side length C. So we use uppercase letters for the angles and lowercase letters for the side lengths. And so for right triangles, we usually kept angle and side length C reserved for that 90-degree or right angle. For these oblique triangles, that is no longer the case. A, B, and C can be any of the angles. All right, so to actually derive the law of sines formula, we need to actually use some of our knowledge of right triangles and make some right triangles show up in the pictures we have here. And so we can do that in our first oblique triangle just by creating this little vertical line. I think we'd call that a perpendicular bisector. So by introducing this vertical line, we can now break our non-right triangle up into two smaller right triangles. And now we can use some of our knowledge of right triangle trigonometry to relate these side lengths and angles together. And so we can actually mimic this process over here for our other type of oblique triangle, but to get that second right triangle in, you'd have to drop your vertical line down from the tip here at angle B and kind of add in this missing triangle. You have to work with some reference angles and complementary angles and things like that, but the overall argument and formula we get from that process is going to be the exact same. So for that reason, we're just going to actually do the proof for this first case of the oblique triangle where all the angles are acute or less than 90 degrees. And so I've gone ahead and labeled this height value h for our two small interior right triangles. And now our goal is to find or express the height h here in terms of these other maybe known angles and quantities. And so, well, one thing we can notice is that if we're working with respect to this angle A, then h is the side length opposite of our angle, and c would be the hypotenuse of this right triangle. And so, well, one of our trig functions relates an angle to the opposite side length and the hypotenuse, and well, that's our sine function, and that should be no surprise. So if we take sine of our angle A, using our right triangle here, sine of angle A is opposite over hypotenuse, or h over c. And if we multiply both sides by c, we find that h is equal to c times sine of angle A. All right, and so we can repeat this argument for our angle C. So how is this side length of h related to our angle C? Well, in this smaller right-sided right triangle, well, we see that h is the side length opposite of our angle C, while in this small right triangle, the hypotenuse is then A. So if we run through this process again, but for angle C, sine of our angle C is the ratio of the side length opposite to our angle C in our right triangle to the hypotenuse of that right triangle, and that'll give us h over A. Well, we can solve this formula for h as well. Multiplying both sides by A tells us that h is equal to A times sine of our angle C. And so now we can start putting this together. We know h is equal to itself, which tells us that c times sine of A, that is our first version for h, must be equal to our second version for h, which is A times sine of our angle C. And so this really is that relationship that we call the law of sines, but we tend to write it in a slightly different format, kind of moving the corresponding pieces around. We can write it as sine of angle A over side length A is equal to sine of angle C over side length C, right? Just divide both sides by A and C to obtain it in this form. And so we can actually add a third side or equation to this formula that gets the side length and angle B involved. The way we do that in our picture is by introducing another one of these perpendicular bisectors or dividing lines. We could do one that kind of cuts angle A in half, or we could do one that cuts angle C in half. It doesn't matter. That would then create two smaller right triangles, one up here and then one down here. And we could run through this process again, maybe call that intermediate value Z. So set up some sine expressions to find Z in terms of these other angles and side lengths, and then equate them the same way we did here. And we'll get the exact same equation, but now involving sine of angle B, side length B, and sine of angle C and side length C instead. And so we find when we repeat that analysis is that we get sine of angle A over side length A is equal to sine of angle C over side length C. And this third piece we're adding on here is that all of this is still equal to sine of angle B over side length B. And this formula is what we refer to as the law of sines formula. All right, so I've gone and rewritten our large version of our law of sines formula over here. And really we look at it in two forms. The first is similar to what we saw before. Sine of A over side length A is equal to sine of B over B, which is equal to sine of C over C. Or we could flip over all these fractions involved in our law of sines formula and write it with the side lengths in the numerator instead. And that looks like A over sine of A is equal to side length B over sine of angle B, which is equal to side length C over sine of angle C. In this example, we are asked to solve the oblique triangle that is given. And so in this triangle, we are given angle A, which is 20 degrees, angle C, which is 25 degrees, and side length C, which is 80.4 units. And so in this triangle, we know two of the angles and a side length opposite of one of them. And so that's a situation where we can use the law of sines to find the rest of the information about this triangle. Remember, when we were asked to solve a triangle, it means we need to find all the side lengths and all the angles. So for these missing or unknown side lengths and angles, we need to state them in order to solve this triangle. And so to finish solving this triangle, we need to find angle B, side length A, and side length B. And well, for one of these quantities, we don't need to use the law of sines at all to find it, and that is our missing angle, angle B. We still have the fact that all the angles in a triangle have to add up to 180 degrees. So our angle B will be 180 minus our two known angles of 20 and 25 degrees. And so using that fact, we can pretty quickly find that our angle B is going to have to be 135 degrees. One thing we might want to notice now is that in a lot of these oblique triangle problems, we're working with degrees instead of radians. So if we're going to have to evaluate a trig function for any of these problems, we want to make sure that our calculator is in degree mode and not in radian mode. All right, so we found our missing angle B. Now we have to find our missing side lengths, little a and little b. And it doesn't matter which one we find first here at this point. So let's go ahead and do it alphabetically and start with little a. And so to find side length A, we're going to have to use the law of sines. And so remember, there's two versions of our law of sines where we either have the side lengths in the numerator or the denominator. It doesn't actually matter which version you use, but I always put the unknown quantity, the one we're looking for, up in the numerator. That just makes us have to do one less step of algebra. It makes it a little bit easier to solve for once we plugged everything in. So we're trying to find side length A. So we have A over sine of A, and now we're going to set that equal to either side length B over sine of B or side length C over sine of angle C. And to make that choice, it really depends on what information we know. And well, we don't know side length B yet, so that kind of forces us into using our law of sines version, where we have A over sine of A is equal to C over sine of angle C. And now at this point, we can plug in all the information we know. Well, we don't know side length A. That's what we're looking for here. We do know angle A. Angle A is 20 degrees. So our denominator is going to be sine of 20 degrees. We'll have to use a calculator to evaluate that at a later step. And so for the right-hand side of our equation, we have to have side length C, which was told to be 80.4. That is divided by sine of our angle C. Angle C is 25 degrees. So our right-hand side is 80.4 over sine of 25 degrees. Well, now we can solve this equation for A, and so we see that the exact value of A is going to be 80.4 times sine of 20 degrees divided by sine of 25 degrees. All right, to solve for a in this equation, I just multiply both sides by that denominator on the left-hand side, sine of 20 degrees. And that's why I said we want to have the unknown quantity we're trying to solve here in the numerator. Otherwise, you have to also do a step of reciprocation or flipping the fractions over. All right, and so we can evaluate this quotient in our calculator. 80.4 times sine of 20 degrees, then divided by sine of 25 degrees, gives us a value of about 65.1. So our side length A, we'll say, is about 65.1 units in length. All right, and so now we need to use the law of sines one more time to find that last side length of B. And so let's go ahead and think about what version of the law of sines should we use. So we're definitely going to want to have B in the numerator, because that's the unknown quantity we're looking for. That forces us to have sine of B in the denominator. And now we need to set that equal to A over sine of A or C over sine of C. Since we basically know all that information, we can do either one and get essentially the same answer. Although one thing to notice is in our value for A, remember we rounded a little bit. So if we were to use A over sine of A in this next part, that rounding error would also get compounded and introduce even more error into our side length B value. So for that reason, I think it's better to actually use side length C, that given possibly exact piece of information, over that rounded piece of information that we found. So we're going to set B over sine of B equal to C over sine of angle C. So let's go ahead and plug in everything we know. Well, we don't know side length B, so that's what we're going to solve for. We do know angle B is 135 degrees. And that's going to be equal to side length C, which we were told was 80.4, divided by angle C, which is 25 degrees. Or sine of angle C, which is sine of 25 degrees. Okay, so now we can solve this equation for little b by multiplying both sides by sine of 135 degrees. And we get that little b, or side length b, is equal to 80.4 times sine of 135 degrees divided by sine of 25 degrees. And we could find the exact value of sine of 135 degrees using our unit circle, but we're going to have to approximate that value of sine of 25 degrees anyway, so let's not bother. When we plug all this into our calculator, we should end up with side length B being about 134.5 units. All right, so we have finished this example off. We've solved this triangle because now we know all 6 quantities, the 3 side lengths and the 3 angles. The 3 missing quantities were angle B is 135 degrees, side length A is 65.1 units, and side length B is 134.5 units.